Thanks so much for having me. And yeah, I really appreciate these Google Earth Engine meetups, and they benefit me a lot. And I hope I can share some things here that interest some of you and inspire some of you. But yeah, today I'm going to be talking about work. Three papers I've written this year that use Google Earth Engine, and two of them focus on the effects of the lockdowns on human activity and the environment. And this is work-based. It's work that originated partly from my work where I'm currently based in Norway at the Norwegian Institute for Nature Research, but also some of it originated through my work under my capacity as a consultant at ZSV Consulting in South Africa. I'm originally from South Africa. I finished my PhD there in 2018, and then got a job as a spatial ecologist at Norwegian Institute for Nature Research, or NINA. What to expect from this talk. I think it's going to be broken down into three parts. That reminds me, I must set my timer to keep track of time. But the first part, I'll be presenting a paper where we looked at the response and recreational activity in Oslo, the Oslo municipality, during the coronavirus lockdowns in Norway this year. The second part, I'll talk about I use Google Earth Engine and other open source data to monitor global air quality changes during the COVID-19 lockdowns. And finally, I'll present some work of using Google Earth Engine for sort of social justice agenda, and where we mapped South Africa's green apartheid using sentinel imagery and socioeconomic data. And I'll explain later what green apartheid means. But this talk might be a bit of an information overload, because I'm going to sort of a high level overview of these papers, and just to maybe spark ideas, and you're welcome to contact me afterwards with more specific questions. But I'll be focusing on the results and sort of data visualization. It's a lot with Earth Engine, but also with R and things like ggplot, those packages in R. So take away the bits that inspire you. But so I'll start with this map, which shows the stay-at-home requirements that were enforced during the COVID-19 lockdowns this year. And this is as of the middle of May 2020, and the map is colored with the increasing heatness of the color, or the red areas have extreme stay-at-home requirements. The gray areas have no stay-at-home requirements. And if I play this time lapse of how this sort of expanded over the globe, it obviously tracked the spread of the COVID-19, and as cases increased in different countries, they started requiring people to stay at home in some places, but in other places it wasn't a strict requirement, and it was more of an advisory. But you can see how quickly virtually the whole globe turned red in this map. But interestingly, Norway and Sweden were sort of two rebel countries that bucked the trend, and they were like, no, our population is somewhat low density, so we can afford for people to spend time outside and safely social distance. So in that way, it provided some kind of natural experiment, and we were interested in seeing how it affected people's use of green spaces in and around Oslo. And this is a map, a graph showing data from Google mobility reports for Oslo municipality, and on the y-axis is the change in percentage since the baseline. And you can see that as lockdown, stay-at-home advisories in Norway were enacted by the government, there was a massive decrease in the visit to workplace, to transit stations, to retail. But interestingly, there was an increase, of course, in the visitation to residential areas because people stayed at home, but also to parks and green areas. So we saw this trend, but we wanted to quantify it in a more spatially fine-grained way. And So we published this paper in Environmental Research Letters, where we used Strava mobility data. So Strava is a mobile application that people use to monitor their fitness activity, and it predominantly includes cycling and running, but also in winter skiing and also water sports activities. But in this time lapse, you can see that this is showing the diurnal pattern of recreational activity, recreational intensity based on the color of the line segments. And as lockdown hits, you can see that there's an increase in the sort of the heartbeat of Oslo gets stronger and extends further into the surrounding forest. And the graph on the top here shows the activity for 2020 in blue relative to the activity for 2019. So overall, we found a 291% increase in recreational activity relative to the baseline. And I'll go into a bit more detail on how we calculated this. So these are just, in a sense, static versions of the animation that you saw above, but broken down into pedestrian activity and cycling data on the activity on the right. And here, the line segments or the recreational trails are colored by the change in the number of activities per day. So anything in red is showing an increase in activity, anything in blue a decrease. And you can see for pedestrian activities somewhat heterogeneous over space. For cycling activity, it was almost an increase throughout the city, which was interesting. And in the discussion of our paper, we hypothesized that it was due to, of course, public transport wasn't very active, and people used bicycles to commute around. Well, let me just go back and say that we wanted to, of course, recreational activity is determined to some extent by the predominant weather at the time of year, whether it's a holiday or not. So we wanted, instead of just using a simple subtraction of 2020 activity, subtract 2019 activity, we wanted to try and account for the weather effect. So what we did was create a weather benchmark model, which essentially was a multiple linear regression of time series with recreational activity as the response variable, and then a bunch of meteorological variables as explanatory variables, and time of year, and whether it's a weekend or weekday or holiday or not. And then we could model what we would have expected the recreational activity to be in gray here with these error margins around it. And in purple is the 2020 observed recreational activity. So you could see that it was higher for both running and walking, and cycling was higher than what we would have expected given the time of year and the weather during the lockdown dates in March. Putting it in real numbers, recreational activities increased from about 28,000 to over 100,000. There was a large increase in the percentage of Oslo's population using these areas, and a greater increase for cycling relative to pedestrian activity. And we actually also used counter stations. So these are devices that you put along strategic places along trail segments that count the number of people that pass. So we use that to calibrate the Strava data, given that the Strava data is only represents a subset of society at large, or it's a subsample of the population. This is just putting it in a global perspective. This is the same map as you've seen before, but this is showing visitation to parks and outdoor spaces using the Google mobility data. And you can see that Norway, Denmark, Sweden, Finland, essentially the Scandinavian area sticks out like a sore thumb, where there was an increase in visitation to outdoor spaces and parks, whereas virtually the rest of the world, except for Mongolia, interestingly, I don't know what the mechanism is there, but virtually the rest of the world had a decline in visitation to parks and outdoor spaces. And there have been similar papers in the United States looking through survey data, not through mobile tracking data, but also observing this decline in recreational activity, which was in contrast to what we found in Norway. But so now I'm going to move on to the next sort of section of this talk. And although there was this increase in recreational activity in Oslo, at the global scale, there was a decline in visitation to green areas, but this was because people stayed at home under the lockdown advisories, and there was a general decrease in the visitation to workplaces as measured by the Google mobility data. So all the blue areas show a decline in the visitation to workplaces. So this is an unprecedented situation in history, and it really raises some interesting questions. It provides some form of natural experiment where we can see the impact. It presents a real life counterfactual scenario, which is counterfactual to the business as usual, where people go to work and use public transport and economic activity continues as normal. And one of the obvious things people noticed during this time was the consequences it had for air pollution emissions and air quality. And this is just an image of a street in New Delhi, India, illustrating the stark contrast. So this is the sort of business as usual, and this was the same street during lockdown. Of course, no people and cars on the road and much clearer skies. So this is at one level quite an obvious effect, but as many of you know, a lot of what we do in science is try and prove the obvious, or at least reduce uncertainty about things that people note anecdotally. So I thought it would be interesting to try and quantify this on a global scale, given that in Google Earth Engine we have data from Sentinel-5 that measure various gases in the atmosphere. And at the time, when I was just playing around with the idea, I made these sort of crude time-lapse animations showing the background layers, Sentinel-5 nitrogen dioxide, tropospheric nitrogen dioxide, and the lines are showing the decrease in air pollution in blue and the increase in COVID-19 cases for China and Italy. And this is obviously quite a crude illustration of what happened, and this correlation is by no means causal, but it was obvious that as the coronavirus spread across the globe and governments enacted stay-at-home measures, there was this decline in air pollution. So I used Google Earth Engine for the Sentinel-5 data, but then I thought I wanted to try and quantify ground level air pollution or air quality that's more relevant to human health and human exposure. So there's this really fantastic initiative called OpenAQ, Open Air Quality, and it's this open access database of air quality stations scattered around the world. There are over 12,000 locations covering 93 countries. And incidentally, I took this screenshot from the website last week, and you can see the effect of the wildfires around California, in this case on the PM 2.5, which is small fine particulate matter. So I wanted to use this data to quantify the effect of the lockdowns on ground level air pollution data in combination with the satellite measures of atmospheric air pollution levels. And so the first attempt was simply to calculate the January to May averages for 2020 and subtract a 3-year baseline for those same dates. And on this map is each air quality station, in this case for nitrogen dioxide, so anything in brown is showing an increase relative to the baseline, and in purple, a decrease relative to the baseline. And you can see overall there was a significant decline in ground level nitrogen dioxide, and particularly around China and Central Europe, but also in the States, although of a lower magnitude. And I did this for ozone, which tells quite a different story, where actually we saw an increase in ozone, ground level ozone, over most of the same areas. And later I'll go into a bit more detail about that. And then for particulate matter, it's sort of followed the same spatial pattern as for nitrogen dioxide. Yeah, a large decrease, although somewhat spatially heterogeneous over Europe with some local increases, but in general, a decrease in fine particulate matter. But as with the Strava data, we know that air pollution is determined by multiple factors. Some of the most important ones are, apart from the emission sources, some of the most important determinants of ground level air pollution is meteorological variables like temperature, wind speed, humidity. And so we wanted to, again, account for this. So we, and also we wanted to get a bit more specific about the lockdown effect. So we have this data on the date at which countries enacted stay-at-home measures, so that we use this as a proxy for the lockdown effect. And then we also used data from Google Earth Engine, the global forecast system data set, to get, I played around with ERA 5 data and GFS data, but ERA 5 data had a bit of a ingestion lag, so I couldn't get sort of near real-time data, whereas with the GFS data, I could get that. So we collected data for each country on the temperature, humidity, precipitation, wind speed. And again, we fed this into a multiple linear regression model. I also tried random forest model and some other models, but the linear regression model seemed to explain most of the variance. And so where air pollution was a response variable and these meteorological variables, along with the time of year, whether it's a weekend or weekday, as explanatory variables. So we could come up with a benchmark measure of what we expected air pollution levels to have been during the lockdowns under the prevailing weather conditions. So once after doing that, we produced these graphs. So taking the one on the left here, nitrogen dioxide concentrations on the y-axis and days since lockdown. So this is average across 34 countries up until the 15th of May. And in black here with the error margins around it is the weather benchmark. So what we would have expected the ground level air pollution concentrations to have been. And then red is what we observed. And you can see the obvious deviation or negative anomaly in the nitrogen dioxide concentrations. And we found averaging across all these countries a 60% decline, which is a huge decline in ambient nitrogen dioxide. For ozone, again, the story was quite different, where overall there was an increase of 4% relative to the benchmark of the baseline. And for particulate matter, there was a decline, but it was sort of half the magnitude of what we saw with nitrogen dioxide. And the reason why, so a bit of a disclaimer is that I'm by no means an atmospheric scientist. I've done some work with TC on mapping urban climate, but I had some very good co-authors on this paper who could help explain the atmospheric chemistry and the mechanisms behind these effects. And often there are complex chemical interactions that are taking place in the atmosphere, and when gases like nitrogen dioxide decline, often gases like ozone increase due to titration effect, which I won't go into detail about, but there was some explanation for the increase in ozone. So we published this data in PNAS, and we actually also did a bit of an epidemiological analysis where we quantified the impact on public health, on mortality and emergency room visits and asthma incidents. But that got cut out by reviewer number 2. We've submitted that part of the analysis to another journal, which is still under review. But on the air pollution side of things alone, we found this overall decline, and we also find in the paper, which I haven't presented here, but we found that countries that had the greatest decline in mobility, based on the Google mobility reports, had the greatest declines in nitrogen dioxide and particulate matter. So this showed for the first time some global scale empirical evidence for a direct link between essentially the transportation sector and ambient air pollution. And in our conclusions, we were by no means implying that these lockdowns were sustainable, but it did provide an interesting counterfactual scenario from which lessons can be learned. And the obvious lesson to learn here is that introducing alternative forms of transport, so alternative to the fossil fuel-based transport that most vehicles, or most of us use, we can effect drastic declines in ambient air pollution in cities. And this has obvious consequences for public health. There's between 6 and 8 million estimated 6 and 8 million excess deaths due to ambient air pollution globally every year. So it's a significant public health threat. And then, there needs to be more research done. And I just checked the other day, there's an online document where people are tracking publications on lockdown effects on air pollution, and there's over 130 papers that have been published, mostly local scale, city level or national level. But there's still a lot to learn here about the effects of lockdown on air pollution. Okay, so I'm going to quickly switch to do a little demo of an app that I published with the paper. I didn't think about this. I'm just going to stop and share my browser. Okay, so I'm assuming you can all see that. So we sort of wrapped the data up in this Earth Engine app, as many of you have seen and done before. I found it quite interesting thinking about how to visualize this data in an impactful way, in a simple and impactful way. And I sort of settled on these paneled graphs showing before this benchmark and the lockdown situation on the right, so you can get this visual comparison on left and right. And then I showed the satellite data on the top and the air pollution, the air quality station data on the bottom. And really what I find really intuitive and useful is, instead of allowing people to scroll randomly over your map, to create a drop-down menu with locations that they can explore. So they can zoom to different areas, like here, China. And then you can also select different air pollutants, and update the maps on the fly. And then this graph showing in a similar manner to the manuscript, showing the deviation from the benchmark levels. And I also found it quite useful after feedback from my colleagues to have these buttons here like see legend. So you can click on that, and then it shows the legend, so that if people want to take like a screenshot of the app or something and share it, they can do that, but they can also hide the legends. And then this button swipe map is quite trippy and it's not very intuitive, but yeah, this just turns it, yeah, it's a bit confusing because there are now 4 different ways you can swipe this. So this is the air pollution, the satellite Sentinel-5's direction, and then this is the air quality station direction. And if you want, you can do the air quality station satellite direction. But yeah, that was just a quick overview of the app. So I'm going to switch back to my presentation. Okay, so now changing track completely. Final paper I'll talk about is where, yeah, I find it quite meaningful and exciting to do this paper. Yeah, and in a sense, it's using Google Earth Engine and remote sensing for some form of social justice. So it's some form of science advocacy in a way. Although after my experience with this, I realize it's very tricky to cross the line between sort of pure science and yeah, communicating a political message with your science. And it's something that maybe I won't do again in the future. But anyway, just to provide some context, I'm sure most of you know that in South Africa we have a history of apartheid, and that is a term essentially defining the separation of races in space and in time. And yeah, it was a form of oppression against, these are terms that were used under the apartheid system, but Black African, Indian, colored, and other, which sort of included Chinese and other races, in contrast to the white population. And the white population were the perpetrators. And of course, this is mirrored in many parts of the world with colonial history, slavery. But in the global north, so in places like America and Europe, people have noted a discrepancy in the distribution of urban green space along these race and income lines. But not much work has been done on it in the global south. And South Africa is one of those countries or places. And growing up in South Africa, I noticed a lot, you're constantly faced with these scenes of inequality, whether it be housing density or the apparent income status of a neighborhood. We can go literally within 100 meters, like in this picture over here, this dense informal settlement, and then this luxurious golf course. Yeah, within a few meters, you can change worlds completely. And so I wanted to try and quantify this. And this is a little bit using the new Google Earth web, where you can fly in to locations and do this panoramic, I don't know what to call it. But this is flying into a place in Cape Town. I'm switching now to a drone image of this contrast, where on the top part here, you have a gated estate, a gated community with really nice green spaces and blue spaces, water. And then just across the way, there's this really dense, low income area with virtually zero green space interspersed amongst the houses. So yeah, I wanted to try and map this, and using Google Earth Engine, it's possible to do this on a national scale. So I use this screenshot of the Google Earth image of a suburb in Cape Town for illustrative purposes to show the methods. So the first thing I did was calculate NDVI, which I'm sure all of you are familiar with, to get a measure of vegetation and greenness, how luscious and vigorous the vegetation is. And here I use Sentinel-2 at 10 meter spatial resolution, because I wanted to separate out private space from public space. And here public space I defined using using a road network, so road verges and road islands, and then also parks and other public spaces. And then the matrix in between in this image is mostly private gardens. And then, yeah, so I measured NDVI within the public space and then within the road verges, but then also within parks. And here I used OSM, OpenStreetMap data to define parks and measured NDVI within them. Then I also measured tree canopy cover. So here I used a machine learning, a random forest model, a regression model to predict fractional tree cover using a training data set where I manually classified sentinel pixels based on their fractional tree cover from visual interpretation of high resolution, very high resolution satellite imagery. And I trained a random forest model with sentinel data as features driving it to predict spatially explicit tree cover, again, within private space, within road verges, and within public parks. And then I also used the park geometries, measured the park size, and then also the proximity to a park. So for every pixel, I used, calculate the Euclidean distance. It would have been nice to use a routable road network to actually work out the distance along a road path, but I didn't have that, so I just used the Euclidean distance to the park. And then so we have that sort of geospatial data on the green spaces, and then on top of that we have this census data for South Africa, and we extracted urban units defined by the census data as urban census tracts. And for those we have the population group into the Black, African, colored, Indian, and white. And we have the household income reported for those census tracts. So we could overlay that with the green space data to see how they correlate over space. And this is sort of a summary across the whole country. And starting on the left here, the share of the urban population. So let's take the white population. They constitute about 16% of the urban population, but their share of the income is massively disproportionate, where they actually have a 60% share of the income. And share of the urban greenery, they have 30% share, so double what you would expect given their population size. In contrast, the Black African population have a 70% share of the population, much smaller slice of the income, and a very small slice of the urban greenery. So that's sort of a high level telling a story of inequality over the country, but we also plotted this data. So each dot in these graphs is a census tract. And on the y-axis here is we quantified NDVI for each census tract relative to the city mean, so that we could compare cities in the very arid, dry parts of the country with cities in the mesic green parts of the country. So on the x-axis is per capita monthly income, and you can see that as you increase in monthly income, there's a general increase in the relative greenness of the census tract. This is mostly true for almost all the race categories. And similarly for distance to the closest, this is tree cover on the y-axis. You can see that virtually the same story, where as you increase in income, you're more likely to have higher tree cover in that census tract. And perhaps the most striking finding was that we used the Landsat satellite archive to go back to 1990. In South Africa, democracy was instituted in 1994. Apartheid sort of ended between 1990 and 1994. And on the y-axis here is again the difference in the census tract greenness relative to the city mean. And each line is colored by the race category. And you can see that, interestingly, since apartheid, the gap or the spatial inequality has been magnified or increased. So the white population have increased their share of the urban greenery, And in contrast, the Black African population have lost their share of the, somewhat lost their share of the urban greenery. So you would obviously hope that over time, all of these lines would converge in the middle, where green space would be more equally distributed across race and income categories. But sadly, this is not the case. And I don't have time to go into the reasons for that, but in the paper, you can read about that. And so, yeah, we sort of concluded, and the reason why I used the term green apartheid in the title, which was quite controversial and got a lot of pushback from the general public. But I sort of stand by it because green inequality is really rooted in apartheid geographies. And sort of to talk about spatial inequality without acknowledging the past is naive and ignorant, quite frankly. And we have to acknowledge the past, but at the same time, we can't blame the past constantly. And we have to, this current government to some extent has to take responsibility to try and address these spatial inequalities, but it's also up to civil society to do the same. And yeah, I thought it interesting to reflect on how have we as individuals perpetuated these spatial injustices. And I know that these inequalities are evident in America and in Europe, and I'm sure in the parts of the world that you're all from. So yeah, we published this in Landscape and Urban Planning, and you're welcome to go and read it there to get more details. But I think I've got a few minutes left. TT, just tell me if I'm wrong, but I'll quickly just demo the app that I published with this paper.
It's fine, like 3 minutes.
Okay, 3 minutes. Okay, so for this app, I also went with this sort of split panel approach. It was quite challenging to, cartographically to try and visualize these three layers. I played around with trying to visualize them on top of one another, or with points, size of the point representing the greenery or the income. But I eventually settled on this, which, we have the population, dominant population, just stopping my timer. The dominant population class per census tract on the left, then the share of the income status in the center, and the greenness relative to the city mean. And again, here I used this mechanism where you can jump to different cities in South Africa, and you can also zoom in. And I thought it was quite nice to switch between raster and vector data. So as I zoom in beyond a certain zoom level, I represent the population with points, indicate each point as 10 citizens allocated to each race class. So just another way of visualizing the data, but then also allowed one to update the graph for this area. So it fetches the map extent of these little windows and then updates the statistics for that area. And then, again, I had this button to hide the legends or show the legends, to hide the graphs or show the graphs, which people found quite useful in terms of taking screenshots or just clear. Often these apps can get a bit cluttered, especially on laptop screens. So it's nice to allow the user to clear objects on the map. And then, I added this swipe function again, where one can swipe between the different maps. And it's also nice, especially when you publish an app linked to a paper, to have a little notes button at the bottom where you can have some disclaimers and a link to the publication, which interestingly seems to have disappeared. Yeah, I need to change that. But yeah, I think I'm just quickly going to switch back to, I'm virtually finished, but Okay. For some reason, my PowerPoint is not coming up on the share screen. Okay. I can't get back to my PowerPoint, but I was essentially finished, and the final slide was just saying that you're welcome to contact me